right, so if we take a look at the notes, I'm going to now show you how we write it and what everything means. It's very important that you understand what's the difference between strong and weak. Okay, so the definition of a strong acid is an acid that ionizes, remember to use that word, almost completely, and even some textbooks still say completely. Okay, I think they're a little bit fastidious in IB, and we say almost completely in an aqueous solution. So almost completely. Now remember, words mean a lot here, so you could probably get 2 marks for this, or even 3 marks if they mark the word ionizes almost completely and aqueous solution. If you don't have that aqueous solution, that doesn't mean anything. Okay, it's in water. All right, so complete the reaction below by adding the relative arrows and phase symbols. Okay, so what I want you to look at is, I'm not really worried about these because these can be gases, and maybe we should just put them as gases. Okay, so let's put it as gas. This is then a liquid. These would be in aqueous because they're in water. Okay, and they've been dissolved. All right, so I'm not going to do the rest of them, but as long as you know they're all going to be like that. Okay, so now because of nearly almost all completely ionizes, I'm going to have a big arrow going forward and a little arrow going in reverse. So that shows you that it could make some HCl molecules, but on the whole there are a lot of ions in the solution. So most of the HCl ions in water have become hydronium ions and chloride ions. Okay, so again, this one we're going to have a large forward reaction with a small reverse, large forward, small reverse. Okay, so that you can see that you can have a little bit, like we saw in the video, you can have a few of those molecules in solution, very few, whereas the majority of it has broken up into this, okay, or has ionized into those. So the reaction is slightly reversible. However, the strong acid ionizes so well that nearly all of the molecules, just notice the words I'm using, they're molecules, okay, molecules are those, not ions, of acids are ionized. The forward reaction is very much favored, and so there are a lot of hydronium ions in the solution. Okay, and so we can start looking at a equilibrium constant here. Okay, and because it is slightly reversible. If it wasn't reversible, you couldn't use the Kc values. But instead of Kc values, when dealing with acids, we're going to talk about Ka values. Okay, so we write the expression. So for the first one, now remember, you never write liquids. So it is products over reactants. So I suppose we should balance this. Hey. Okay, that's going to go there. There's going to be 2 of those and 2 waters over there. The others should be balanced because that one goes there and creates 1. But 2 of those go to 2 of those, giving you 2 of those. Okay, it's still with 1 of those. So that's balanced. So the first reaction is H3O plus times Cl minus over, and your product, your reactant would just be the HCl. Remember, you don't put the water because you never put your liquids in the Ka value. So there is our expression for that Ka. Now, if we do the next one, it's going to be the same, H3O plus Cl minus over HNO3, the concentration. Okay, and then the last one, we will have H3O plus squared SO4 2 minus all over, and our molecule is H2SO4. Okay, and we don't worry about our water. Okay, so there are our expressions. So what I'm saying to you is that if the forward reaction is favored, that means we're going to have quite high values of product, which means our top value of the fraction is going to be much bigger than the bottom. And so we are going to get quite high values of Ka values for strong acids. Okay, so I'm meaning greater than 1 here because the top must be greater than the bottom. Okay, and so we're looking at greater than 1. So it says the strength of the acid can be identified by its conductivity. Okay, so conductivity, what does that mean? Well, if we had to think about putting electrodes in a liquid or a solution, okay, and we can then measure the amount of current or voltage, and we know that this works with electrolytes where you have ions in a solution. Now remember, acids in water create ions, and so we know that the bigger the amount of, or the more ions you have, the better the conductivity. And so a strong acid will have loads of ions in its solution because most of its molecules have become ions, and so the conductivity of a strong acid will be quite high. So you can say a strong acid has a high concentration, high conc of ions, therefore high conductivity. All right, and you can actually, if you use the same concentration of all the acids in water, and you measure the conductivity, you can actually see which one's the strongest and weakest. Okay, so now what do we look at when we talk about a weak acid? So a definition for the weak acid is an acid that only partially ionizes in an aqueous solution. So it doesn't almost completely ionize like the other. So complete the reaction. So what we are going to do is that it actually, and it is a reversible reaction, is your longer one is at the top. Oh, let me do it like that, sorry. Okay, so we do have it like that. But majority, because it does happen quite often, we do just use it as a reversible reaction. Okay, so, oh gosh, I'm sorry, this looks terrible now. Okay, so just make them as reversible, but what is happening is that majority is staying as a molecule. Okay, so when you put, say, this is ethanoic acid, you throw this in water, the majority of it stays as ethanoic acid, and then a few of it, only partial amounts of it, will ionize then. Okay, will react with the water and cause it ionize, and that's what makes it a weak acid. It's not that we're saying you're a weak acid, so you have to react like this. It's saying I react like this, and therefore I am a weak acid. Okay, so weak acids only partially ionize, so very few of the molecules of acids ionize. The reverse reaction is very much favored, and so there are a few hydronium ions in the solution. I do want to make this one longer actually, but I don't want to get stuck on this. Okay, so if they put it like that in the exam, I don't want you to have to panic about it. Okay. So if we write the expression here, again, we've got liquids over here and we've got our molecules. I just want to show you that you must put your, what happens that the ions go at the top. And so your products, COO negative, and your CH3COOH goes underneath. Okay, this is sulfurous acid, so this is the weak one, and this is also going to make 2 hydroniums over there. So again, remember, even though it's making 2 hydroniums, oh, sorry, I'm busy talking and writing. Even though it makes 2 hydroniums, it doesn't make it strong because the sulfurous acid doesn't break up into that so easily. Okay, so that's what makes it weak, is that yes, sure, for every one of those it will make 2 of those, but not most of those are not going to break up, and so that's what makes it weak. Okay, H2SO3, it's a sulfurous acid, and then we've got nitrous acid. Okay, it's with the nitrite. But you notice that the ites are making the ous acids. So if you've got a sulfite, you're going to make a sulfurous acid. Okay, a sulfurous acid, and a nitrite making a nitrous acid. A nitrous acid. Okay, so in the eights, the sulfates will make an ic acid, so sulfuric acid, and the nitrate will make a nitric acid. So the ones with the least oxygens make the ous acids. Okay, I just need to put the 2 over here, and then we've got this one, which will be H3O plus NO2 minus all over HNO2. Now what we're looking at here is that because majority are staying as their molecules, this is going to be high over here, and so we then get a very low Ka value because your fraction is bigger at the bottom than at the top. Okay, and we're looking at things that are less than 1. Okay. All right, let's take a look at then a strong base. So now this really does pretty much do the same thing, except instead of ionizers, we're talking about dissociates, okay, because it really does break up into those ions. I shouldn't even be putting water over here, okay, because it just breaks up into those. It doesn't react with the water really. Okay, so it really just does break that up. But anyway, let's just take a look. So we will then have strong forward, weak reverse, or forward favored and reverse not really, or only a little bit. Okay, so the reaction is slightly reversible. However, the strong bases dissociate so well that nearly all the molecules of the base are dissociated. And careful about my wording over here. It's actually not molecules, it's ionic compounds. Okay, sorry. I'm just, you know what I did? I probably cut and pasted that. So just change those molecules to ionic compounds. Dissociate. The forward reaction is very much favored, so there are a lot of hydroxide ions this time. Instead of this Kc value, we use a Kb for obvious reasons. Okay, so again, we're going to look at our products, our concentration of products, and again, with bases, it's based on the, oh, excuse the pun, based on hydroxide. The hydroxide gives bases their characteristics. Okay, and then we've got our NaOH. Okay, K plus OH minus over KOH. Okay, last one here. Li plus OH minus all over LiOH. And there we have them. Okay, and again, we're going to have high top values because majority are changing to products. So we're going to have high concentration of products, low concentration of reactants, and so our Kb values are going to be high. Kb values high. Okay, a weak base does the same thing as the acid, except instead of ionizes, it dissociates, so only partially dissociates. Okay, so here we have, see, this is what ammonia did. When you put ammonia in water, the water acts as an acid. So it's just how it reacts. That's why that is there. And that's how come you get the OH minus. Okay, when you've got a ammonia, sorry. So in this case here, they break up. In majority cases, they just dissociate. This one technically ionizes, okay, and there I've put it over there, ammonia ionizes. It's the only one, it's the exception, remember our exceptions. Okay, and so we can do that, whoopsie, where we have, but again, it's mostly reversible reaction. So weak bases only partially dissociate, so very few of the molecules / ionic compounds, because ammonia is a molecule, if it's a molecule, it will ionize. If it's a ionic compound, it will break apart. Okay, the reverse reaction is very much favored, and so there are few hydroxide ions in the solution. So if we had to do this, we would have ammonium ion with our hydroxide over our ammonia. So if you see this at equilibrium, you'll notice that you'll have a high concentration of ammonia, but low concentration of ammonium and hydroxide. And then this one, we have an OH minus 2 and an Mg plus. Okay, with our MgOH2. Please notice that when you have two hydroxides or two hydrogens in acids, that you will end up getting two hydroxides or two hydroniums. Okay, so this is a general rule of thumb. Again, please, this is not set in stone. A Ka and a Kb value, weak acids and bases should be less than 1, and strong acids and bases would be more than 1. And you can rank it like you could have a whole lot of weak acids, but because they could all have a Ka value less than 1, but you can see, oh, this one's closer to 1 than this one, and so this one could be a stronger acid than this one. Okay, so you can compare, but this is generally the rule of thumb. Okay, now I want to just discuss what's the difference between strong and weak and concentrated and dilute. This is so important, girls, that you understand the difference. So remember, concentration is the amount of particles that you put in a liquid. Remember, concentration is number of moles over volume. Okay, the amount of particles per volume. Okay, so what can happen here is that concentration means that there is, if something is concentrated, there is a lot of solute, that's your acid and base particles, compared to solvent. Okay, so here you have a lot of HCl, or HCl being broken up. You can have a lot of hydronium ions, and the water is the gray part. Here you can have very few, and there's the gray part. So this one is dilute. It means we've got a little solute compared to the solvent. We've got more water than reactants or products, and less water, or not less water, just we've got more particles in this one than in this one. That's what makes this one concentrated, this one dilute. So it's exactly like the whole OROS thing. The more OROS you put in the water, the more concentrated it is, the less you put the dilute. But what I want to get at is, just because it's concentrated doesn't mean that it is a strong acid. A strong acid is when it nearly, almost completely ionizes. That is it. Okay, we can have a dilute HCl. If I take a teaspoon of HCl and put it in a liter of water, that's dilute HCl. Okay, even though it's a strong acid, it just means that whatever I've put in there, majority of them are going to become ions. Okay, it's still a strong acid. It has just been diluted, and your pH will read differently then, okay, because your pH reads the amount of hydronium or hydroxide ions. Okay, so concentrated doesn't mean strong. I don't know if I let you smell the ethanoic acid in my lab. It's the very, very strong vinegar smell. It takes your breath away. Okay, and that's because it's concentrated, and if we had to take the pH of that, it would be quite high. It'd be quite low, because it's an acid, but there's a lot of, it's so concentrated that there's a lot of hydronium ions in it. Okay, so, but it's still a weak acid because it only partially ionizes. Okay, so be careful between strong and weak, and concentrated and dilute. Okay, what I'm going to do with you now quickly is I want to do question 6 with you. I like this question. It's actually doing some equilibrium stuff, and then I'm going to let you, I think, no, today I'm not letting you do anything. I think I'm letting you do some stuff tomorrow. I can't remember what the schedule says. Oh wait, it's here. Yeah, you just, on Tuesday, you're just going to do some of the think tank of this, and you can play around with some investigations on the PhET simulation. I'll give you some things to do on there. Okay, so here we have propanoic acid. So they're using some organic acids here, which is perfectly fine. They can do that. Okay, ionizers in water as follows. So here we have propanoic acid. Just notice it's in like a condensed structural formula because this is more molecular, but here they're showing the definite structure, well, condensed structure. Okay, in water, notice the L. Okay, reversible reaction. Here we have a hydronium ion, and we've got the ion from that, which is then propanoate, I suppose. Okay, so a learner dissolves 0.25 mole of propanoic acid in 500 centimeters cubed of water and measures the pH of the solution. This shows that, remember, square brackets mean concentration of hydronium is equal to that. So write down the initial concentration of propanoic acid. So now we need our equations. Okay, so we know C is equal to N over V. They said 0.25 over, now remember, centimeters cubed, we want it in decimeters. So 1, 2, 3, so it's going to be 0.5 decimeters divided by 1,000. Okay, and this lands up being 0.5, if I remember correctly. 0.25 divided by 0.5, and we get a half, yes. Okay, so we get we get a 0.5 mole per decimeter cubed. Okay, I can't fit the unit in there. I'll put a capital M. Okay, all right, so we know that they put in 0.5 moles of propanoic acid, but when they measured the pH, they could then work out, I'll show you how to do that later, they could then see that the concentration of the hydronium ions is 2.55 times 10 to the minus 3. So that means we're moving the 3 spots. So 1, 2, 3. So 0.00255. That's the concentration of the hydronium ions. That means that not very many of those became those. Okay, so that's a very small amount of hydronium ions compared to how many of those moles we put in. All right. So what does the concentration of the hydronium ion indicate? The strength. It is weak. Okay, don't worry about dilute and things yet. They've asked for strength. Okay, so we know we put 0.5 moles per decimeter cubed of propanoic acid in the water. And when we measured that, we only got such a little bit concentration. Okay, write the expression for the ionization constant. So we know we leave out the L, okay, and you go H3O plus, times C2H5COO minus, and we put it over C2H5COOH, which is on that side. Okay, here we've got, now I know I told you must use moles in your ice table, and I do stand by that, but you can actually look at the concentrations as well, especially if the volume is constant here. So what I'm going to do is, we know that at equilibrium, the hydronium ions is that. We got it from up there as well. So that means that we make 2.55. The change was from 0 to that. Now, remember, it's only our change that we use our ratios, but we can see it's a 1-to-1 ratio. So that means that 2.55 times 10 to the minus 3 reacted, okay, because it's a 1-to-1 ratio. And if we take a look, we started with 0.5. Okay, so if I look at it there, I'll try and get you to see that. 0.5 minus 2.55 times 10 to the minus 3. We land up with, I'm just going to write this out, 0.49745. Okay, what do they want? Oh, they want us to work out everything. Okay, so we're not going to worry about the water because we don't even put water in the expression. So let's just work with this. This is also a 1-to-1 ratio, so this will also be 2.55 times 10 to the minus 3. So that is 2.55 times 10 to the minus 3. Okay, so calculate it. So we're going to use that expression over there to put it in. So it's going to be 2.55 times 10 to the minus 3 times 2.55 times 10 to the minus 3 equals, and then I'm going to divide it by this concentration, divided by 0.49745, and I get a Ka value of 1,31 times 10 to the minus 5. Remember, there's no units. So 1,31 times 10 to the minus 5. That is very, very low. I mean, if you think about it, that if you had to do that, you would have to go 0,000 4 times and then 131. So 0,1234131. Yeah, so that's quite small. That's nowhere near 1. It's much smaller than 1. So we're looking at a weak. So does your value of Ka confirm your prediction? We predicted it was weak. Yes, it does, because our Ka value is low. It's very small. And you can say compared to 1. And so it is a weak acid. Okay.